the application, the type of problems. All right, so questions? You want to throw one out? You're hesitant because you asked so many. Anybody? I'm going to move on if you don't.
Ask a question?
You guys conferring who's going to ask? Just tell me the problem so I can get it done. Did you have a problem?
Yes, 3.51. It's two spherical conductive shells.
Oh, okay. Spheres are good, and cylinders are good too. But spheres are, in my opinion, a little more interesting for a couple of reasons. I'll tell you later. You got inner radius A, outer radius B. Go ahead.
They're separated by material with conductivity sigma. Find an expression for the resistance between the two spheres.
I think we did this. We'll do it again if you want. But how many remember doing this problem? This is the standard spherical problem. It's okay. We'll do it again. So what I'm going to do is say this is centered at the origin. This is a radius distance r. And I'll drill a little hole through here and put a current right there from a battery. Have a current I. And then I'll ground this and I'll ground the outer layer. So what this is think of a sphere with an inner surface that's metallized, aluminum or something. Then the outer surface of the sphere is metallized. And there's a small little conductor that goes from outside to the inside placed there. So current is going to flow radially. Do y'all follow me on this one? Current is going to come in through here. You could think of it as a as an isolated thing or something that's insulated, better yet, so that the current can't just flow this way. It goes from here to here and then radially outward. So the current density J is going to be radially outward everywhere. Y'all with me on this, class? Remember the assumptions, how I told you to do this. You assume something. Usually you assume current. I assume current. The next thing I'm going to get is what? The current density. Correct, class? We're in spherical coordinates. We assume a current. Current density is just the current divided by the area it's penetrating. Correct, class? So what area is it penetrating? Well, if I'm at a distance r away, then all that current has to move through that surface perpendicular. Do y'all agree with me? That surface is what? What's the surface area of a sphere of radius r? It's 4 pi r squared. Correct, everyone? All right, so now I take this and I get J, which is a vector. It's going to be I over 4 pi r squared AR. And the units of that would be amps per meter, but I'm going to be a little loose with this because the units are going to, we're staying standard MKS units. They're going to. All right, now, after J, what's the next thing I get? Now I'm going to get E, right? And to get E, I know that E is equal to what? J divided by sigma. Correct, class? And so that's going to be simply equal to I over 4 pi sigma, and then it's going to be r squared AR. And finally, what's the last thing I calculate? I got J, I got I assumed I have J, now I have, well, I'm sorry, yeah, I've got E, correct, class? Now what do I get? Get the voltage, right? And the voltage is always going to be positive, and to get the voltage, you're going to integrate E dot dl. There's a negative sign here, and we could get the limits right, but I know this is going to be a strict positive quantity, so I'm a little lax on some of this. I know it's going to go from A to B, all right, and I'm just going to put a magnitude there. Well, it's going to be equal to the integral of I over 4 pi sigma r squared AR, and then dot dl, and dl in this case would just be dr AR. Alright, and it would go from A to B, and technically there's a minus sign here, but we're just going to make sure it stays positive one way or the other. Y'all follow me? So when we do this, you know, the AR dot AR is 1, correct, everybody? Recap from last lecture. Everybody got that? It's a dot product is 1. When I integrate this, I end up with 1. I get I over 4 pi sigma And 1 over r squared is technically minus 1 over r, correct, class? And then we evaluate it from the upper to the lower. There's another minus sign. Really what I end up getting, put it like this if you want, I over 1 over a minus 1 over b. And that, in fact, would be the voltage, correct? Once we have the voltage, what's the last step to get the resistance? We always know, and this is from your basic circuits course, resistance is voltage over current. That's the fundamental definition. Regardless of what the element is, it could be a light bulb, it could be a serpentine resistor, it could be anything where there's current flowing and a voltage developed across 2 points. You all with me on this, class? So that's resistance. And for this case, what is it going to be? Well, really, I just get rid of the I over there, don't I? So it's resistance is going to be 1 over 4 pi sigma, and then it's 1 over A minus 1 over B, and that's as simple as it gets. Now, I did tell you there's one caveat to this. What could I do to change this to give a different answer that would be very easy for me to do so you couldn't memorize this answer and use it? Make sigma a function of position. Suppose sigma, I don't know, is sigma naught times r, just for kicks. Then this would be 1, r cubed, correct, class? Now the form of the integration changes and the outcome does as well. Everybody on that, just make sure you understand. Don't memorize the formula. That's the stupidest thing you can do. Okay, other problems before I get going. And pay attention to this lecture because we're moving towards capacitance, and both capacitance and resistance are calculations that require assumptions like this. Now, the way he does it in the book, I think, is a little different than I did it, but it's much easier, in my opinion, to assume the current and to get the voltage than assume the voltage and get the current, at least in spherical orbits. Okay, so today, now we're moving out of resistance and we're moving into things that are dielectrics. So we're talking about dielectrics. When I take it, a dielectric to me is an insulator. Think of it that way. There's formal definitions for all this. Good dielectrics are things that have almost no current flowing when a voltage difference is applied across them, and they insulate. Rubber, plastic, styrofoam, mica, diamond, things like that. Well, diamond, if it's doped, isn't a good insulator, but a standard natural diamond's a very good insulator. And it means you can put a huge voltage potential across 2 layers of most insulators and get almost no current. That's the idea. As a matter of fact, air is a pretty good insulator. Do you know what the conductivity of air is? Anybody? I think I brought this up. Conductivity. Now think about, what is the conductivity of, say, copper? I brought this up a few times.
5.7
It's
times
of
10
the order
to
of
the
5.8 times 10 to the 7th, right? 1 over ohm meters. Here, now just contrast this. For air, right here in room, about, sea level, standard, not real high humidity, like about in here, it's about 10 to the minus 14th, 10 to the minus 13th to minus 14th. All right, think of that. That's basically almost 20 to 21 orders of magnitude difference. This air is a pretty good insulator. It's not a super good insulator, but it's a pretty good insulator. You know how you know it's not a super good? Ever take a balloon, rub it, you get charge on there, stick it on a wall. What do you notice? It doesn't stay there forever, right? That's because the charge dissipates by literally the conduction, but charge conducts through the surface, through the air, and it will, at about, the half-life is about 188 seconds down here. And we'll get to that. It's epsilon over sigma. But it's not a super insulator. Now, if you try to put charge in like mica, if you could encapsulate it with mica, it would stay there for years. I mean, mica is phenomenal. There's other insulators that are really good too. They have almost no effective conductivity is what I'm getting at. So when we talk about dielectrics, we're talking about insulators. Now, I'm going to just take you through things. I'll tell you what to write down. Please don't write this yet. All right, when you take a look at the general way that they describe a dielectric, they think a dielectric, and it's true, has a bunch of little dipoles, like such. And this is in your text. And I'm just showing them arranged this way. They don't have to be in order. They could be just arbitrary. You follow me? But the thing with a dielectric is these are locked in place. They can't move about. Unlike, you know, the electron soup in copper, the electrons can move all through the copper. If you could somehow paint one, you could watch it move if you put a current on. These things are locked in place. So an electric field is put there, it stretches these, and these molecules start stretching this way. And the natural state, plus and minus charge centers separate. And when they do, it's like a spring being pulled, and they gain energy. Do y'all follow me on that, class? Now, that's what happens. That means when you have a dielectric, you're going to have something that gains energy compared to free space, because there's a mechanism of storage. And it will cause a couple things to happen. The first is, there's something that they call the polarization constant, or the polarizability. And it's usually just shown as P. Don't worry about this as a material science, more so than electrical engineering. And that's equal to something called chi, which is the electrical susceptibility, times epsilon naught times E. Now, what this really is a measure of how much it stretches. But don't worry about that. This is material science. Wentworth put that in his book just to give you a little bit of an understanding of where a lot of the things we get come from. This is a material science concept. And it really has to do with energy, but I'm not going to spend time with it. But here's the thing you do write down. Now, when we talk about the D field, D, that is something that is charge per meter squared. It's coulombs per meter squared is the units. But the D field is equal to epsilon naught E. Now, epsilon naught is free space epsilon. That's a relationship between E and D if there was nothing, a vacuum. But it's also plus this P. All right? Now, just understand how this came about. This is material science. This has to do with some very fundamental properties of matter. From that, we're coming to this point. And then we find out that D is actually equal to epsilon naught times 1 plus, this is electric susceptibility, this chi term right here, times E. And that's also equal to epsilon naught times epsilon R times E. And this is the one we use right here. Epsilon naught, epsilon relative times E. Usually the equation is D is just equal to epsilon E, and it's assumed epsilon is equal to epsilon naught, epsilon R. So epsilon R is something related to dielectric materials. It would be 1 for air, but it's a relative dielectric. If air is 1, what that really tells me is how much more energy can some material store than air per unit volume. So epsilon relative is 1, and it goes up, and it goes up to astronomically large values for some of these exotic materials. I've never worked with these, but I read about them. Some of the materials have epsilon relatives of like 20 to 40,000. Now these are exotic materials. They're probably not that stable in a general sense, but they're important. And you know, when we get into capacitance, you'll see why, because energy storage is related to this epsilon relative. The larger it is, the more energy can be stored in a given volume of space. And that comes later, but keep that in mind. So anyway, the real thing is this. That's the relationship between D and E. And I did give that to you, but I didn't expound on it. And how its relationship is to dielectric materials and the susceptibility. Now, that itself is no news. I mean, so what? You knew this already. But now we have to do boundary conditions related to this. You've had dielectrics before, didn't you, in physics?
Yes.
Your professors, we talked about, at least in a very basic sense, what insulators are, what conductors are, right? So you already have and most of you have just a handle on it just from your everyday life. So now we talk about boundary conditions. We talk about boundary conditions, what it means is this. We're going to take a look at something that really, we're going to take a very small snapshot of something that's on a very large scale, and I'll try to explain. Suppose this is a surface, all right? I'm showing you a planar surface. It wouldn't make sense to have a non-planar surface. Well, there's two materials. I'll call this material 1 and material 2, being consistent with Dr. Wimmer's book. And I'm going to say that there's an electric field that's going to be uniform in region 1 and 2, but not the same in 1 and 2. So there's going to be some electric field here. It'll have the same value everywhere, call it E1, and some electric field here. I'm just trying to give you a general idea, E2. Now, E1 doesn't change anywhere in region 1, and E2 doesn't change anywhere in region 2, but the two are different. Do y'all follow me in this class? And where they're different begins where this boundary is. So this is like focusing in on a very small planar piece of material. Think of it going, like zooming in from, with a microscope or something. So you're looking at something where the field levels here are the same on that side and on this side. This is not something over a large distance, okay? Now when you do that, there's two things that are always true. If I take that planar piece of material, and I'll call this region 1 and this region 2, and I go ahead and I build this fictitious little, it used to be called a pill box, but I'm just going to show you what I'm talking about. This is going to be a surface for integration, and I'll call that A, B, C, and D. And I'll call this H, and H is going to be symmetric, so the amount of this pillbox above the surface where 1 is and 2 is the same as below. Do y'all follow me? And there's going to be a length here, L. So now what I'm going to do is say, remember, this is just a surface, an imaginary surface, or imaginary path, actually, not even a surface. So if I take a look here, I know I have an E field here. I'm going to just show you the tangent component of the E field in region 1. It's going to be in this direction. I'm trying to show you just, if you take a look at the E field in region 1, the tangent component would be the component, the projection of the component on that path length from A to B. Can you all see this? And down here, I better make that a little more clear. I'll try to make that a little bit clearer. So what I'm really saying, this is A and this is B. There is going to be an E field from the tangent component in region 1. That's the projection of the actual E vector that's tangent to this surface that separates 1 and 2. Down here, there's also a tangent component, but it would be E tangent 2. Y'all with me? Remember, those are just projections of the vector. The vector is the same everywhere down here, everywhere up here. Y'all with me? Now, we know that the integral of E dot dl from A to B, and I can put a minus, actually there is no minus sign if I do it this way, that's VB minus VA. So that's what E dot dl would be, right? That's a voltage difference between 2 points. Do you agree with that, class? Well, what happens if A is B? What is VA minus VA? 0. Right, 0. Now, what that means is anytime you take the integral of E dot dl around a closed path for this type of electric field, you get 0 volts. And that should make perfect sense. There is no difference. This is called a conservative field. So, what it's really saying is the closed integral over any path of E dot dl for electrostatic fields, this symbol right here just means it's the integral over a closed path. This is equal to 0. So what we do down here to apply that concept here to get the boundaries, and this is one method, is we let h go to 0. So I'm going to say take the limit as h goes to 0 of the integral of E dot dl around that closed path that I've got there from A, B, to C, down to C, D. So it means the height of this thing shrinks to nothing. Y'all follow? When you do that, you find that the top path integral, the integral of the tangent value of the electric field in region 1, from here to here, and just say the dimension of length is L, would be just ET1 times L. Times L. I'm not going to, in the past I've done formal integration, but it tends to detract from the simplicity. So y'all with me on this? Now, when we come down here, this is going around the closed loop. I'm starting here, I'm going here. It's a positive. The E field's in this direction, tangent component. From A to B, it would be a positive value. Now I come down here, this distance is minuscule, so there's no contribution. Now from here to here, E2 is in that direction, but DL is in the opposite direction. Y'all follow me? So it's negative. That equals 0. Just by looking, what do you notice about E tan 1 and E tan 2? They've got to be the same, and that's the general rule. This is called the tangent component of the electric field between any two surfaces is the same, or the tangent component in region 1 is equal to the tangent component in region 2. It's used, the common way they express it is E tan 1 is E tan 2. How many have had that before? You've had in physics? Did you get it? All right. Tangent value of the electric field is always the same across the surface, which is kind of nice in a sense. It makes it real easy. So if you have a perfect conducting surface, you can't have an electric field that's tangent, or you'd have an infinite current. So E tan is 0. Therefore, the tangent field just above that perfect conductor is 0 as well. Now, for the normal component, and I'm going to do it over here too. And this is at a surface. Normal component's a little different because you can have charge residing on a surface. So our charge density. So go back to the same surface. Here's region 1 and here's region 2. Now, I'm going to start with the simplest example. If you assume that the charge density on this surface is 0, okay, then something interesting happens. Now, I'm going to show you my surface. It's going to be like this. Here's a pillbox. It's got a height h, and it's got an area a, and the area is the same in both. So it's a cylinder, right? Now there's a D field up here. There's a D field, a normal component of D field in region 1. There's also the normal component of the D field in region 2. I'm just saying you would take the E field, then you would take the projection of the E field in the normal direction, then you would have to go ahead and multiply by epsilon in that region to get the D field. Y'all follow me? That would be the normal component of the D field. And you know that the integral of D dot ds over the closed surface is Q inside it, right? Remember that? What's that law called? He's my favorite mathematician. Y'all with me on that? That's Gauss's law. All right, and that's true. How much charge is inside this region if rho s is 0? It's not a hard question. No charge density, no charge density, 0, right? So if this is 0, right? I'm doing the special case because this is the one that's most important. I'll do the case where there isn't charge density, it's non-zero. Then the integral of D dot ds is going to be 0, and if we take the limit as my pillbox height goes to 0, so I'm going to crush it down, Then I really get the integral of d dot ds over this surface, so that would be d normal 1 times a, right? But look, now the integral of d dot ds over this surface, if I have the d field just arbitrary, the normal vector is in the opposite direction. Do you see that, class? So it would be minus d normal 2 times a equals 0. Now what can you conclude from that? I'm being casual about this. I want to focus on what the real concept. D normal 1 is D normal 2, right? The only way that can be 0 if A is the same, because I'm crushing that pillbox, so the overall area's magnitude is the same, right? It means D normal 1 is D normal 2. And this is across the boundary, right here. So you've got E tan 1 is E tan 2. D normal 1 is D normal 2, all right? Now there's one case, and this is a special case, and it is if there is a charge density between these surfaces. This one I'm going to write down. I don't hold your feet to the fire on this one a lot of times, but you should appreciate it. Suppose now here's region 1, here's region 2, and I have a charge density that resides on that surface, some non-zero value. Well, now I can develop the same exact equation as I did before here, right? And I can say, but instead of 0, now that's QS. You all with me on this, class? And then I could go ahead and find out that D normal 2, or D normal 1 minus D normal 2, I'd have to, it would be actually equal to the charge density, but I have to be careful with signs, and I'm just going to give you the fundamental end result without taking you through a lot of the mathematics. If you have a vector, a unit vector A that goes from region 2 to region 1, so it points from region 2 to region 1. If I go ahead and I take A21 and I dot it with the actual total D field in region 1 minus the D field in region 2. Now this dot product will give me the normal. Y'all see that? A is perpendicular to that surface, right? So if you dot product that, a unit vector, into the D field, you get D normal. Y'all see that, class? Just take a look at this. A21 dot D1 would be D normal 1. A21 dot D2 would be D normal 1 with a minus sign, because it would be it would actually be the areas pointing downward. That would be equal to the surface charge density. And that is an equation in his book. He has a better picture of it. His picture is on page 188, if you look at it. Now, don't let that scare you. This is not hard right here, but there's one thing you've got to appreciate. You have to have in your head, you got to be clear about what is tangent and what is perpendicular. And you have to be clear what the D field is and what the E field is. So, let's do a simple example. Then I'll get into, then you get your quiz, because I don't have time. I'm going to do a simple example. So in drill 3.29, does anybody else have a book? Can you read this to me? It's drill 3.29. You have two surfaces, right?
Yes.
Go ahead.
For rows greater than or equal to 2 meters, epsilon relative 1 is equal to 2. And E field 1 is equal to 3A row.
This is region 1, right?
Yes.
And what, epsilon relative, what?
Epsilon relative is equal to 2. And the E field is equal to 3A row plus 6A phi plus 9AZ.
Okay, volts per meter. All right.
And then the second surface for row greater than 2 meters, it's epsilon relative is 3.
Hold it. Greater than?
Yes.
Oh, this is greater than 2 meters, less than 3? Did you say row?
Rows less than or equal to 2.
Oh,
Yes,
so-
yes, I did
wrong.
go backwards, yeah.
Alright. My bad. Row less than or equal to 2 meters, so it's the inside. Go ahead. Row greater than 2,
Is epsilon relative is 3,
and this would be region 2, right?
yes.
Epsilon relative equal 3, and they want the E field in region 2.
Yes.
Alright, so what does it look like? Think of a cylinder. Z-axis. Here's rho, here's the defining point. It's going to be 2 meters, right? Outside of 2 meters, inside of it is going to be region 1. Outside of it is region 2, right? You all agree with this? So we got a cylindrical surface. Please watch this carefully. This is a great showcasing problem. So we've got a sleeve, a cylindrical sleeve, right? Look at that E field in region 1. Now you know E tan 1 is E tan 2, correct? All right, what is the tangent? What is the normal component? Normal is always perpendicular to the surface, right? Can you all see that this is the actual perpendicular component to that surface? The rho component, because the surface is at a constant, the dividing surface is it's really a cylinder, isn't it, class? Everything outside a cylinder is region 2. Everything inside that cylinder is region 1. Do you all see that? So that's the perpendicular component. Therefore, this would be the tangent component. Do you all agree with that? The tangent has to, when I say tangent, if you're not familiar with that terminology, if this board is a surface, if the marker was in the plane of the board, it would be tangent. If the marker was perpendicular to the board, it would be the perpendicular or normal component. You all understand that, class? So look here, this is perpendicular to the two surfaces, right? This, therefore, and if you look at it, Z is obviously tangent, right? Phi is tangent too. So this is the tangent component. Therefore, this is E normal in region 1, and this is going to be E tan in region 1, right? Now, what do we know about the tangent component across any two surfaces? E tan 1 is equal to E tan 2. Therefore, we know the tangent component in region 2. Right outside there, we know E tan 2 would be simply 6A phi plus 9AZ, right? And the normal component there is in region 1, right? But we need D normal, right? How do we get D normal? D is equal to what? Epsilon E, correct, class? So we have E, we need to multiply E by epsilon relative in that region. Do you all agree with me, class? So what is epsilon relative in that region? I would say, now I'm going to say D normal 1 would be equal to 3A rho, right? Epsilon relative in region 1 is 2, so it's times 2 epsilon naught. Now that's D normal in region 1. Do you all agree with that? D normal in region 2, well, would be what? Well, it would be, what's epsilon relative in region 2? It's equal to 3, right? So it's 3 epsilon naught, and this would be D normal in region 2. And it would be in the A phi direction. Or it's A rho direction, pardon. Now take a look at this. That is D normal. You all agree? In region 1.
It's not epsilon naught, right there.
Yeah, epsilon naught's going to cancel on both of these. Because you can cancel at the beginning, but I tend to put it in just for completeness here. So it's going to be 2 epsilon naught is epsilon in that region times the E field would be the D field. Correct, class? Over here, I got everything but the D field. So how do I get the D field? You can see it with your own eyes. I just do why. The only thing I do is get rid of epsilon naught, right? And then, well, I got 3 times 2 divided by 3, or it is 2. You all see that? So that means D field in region, D normal in region 2 is equal 2 A rho volts per meter. And from that, what's the E field? Actually, pardon me? It would be what? If you got D, how do you get E?
Isn't that E currently?
Actually, I'm sorry. This, let me do it. What you said is correct. When I take D is equal to epsilon, or I'm sorry, D is equal to epsilon E over here. That was the E field. I'm sorry about that. Then this would be, because they wanted the E field, it would be 3 epsilon naught. That's the epsilon out there times E normal in region 2, and so that would be E normal. Region 2 would be simply 2 A rho volts per meter. Therefore, if you add this to this, you get the total field in region 2. I'm sorry about that. And I'm trying to hustle, because I gotta give you a quiz, and right now, I'm gonna have to have everybody separate. It's gonna be an easy quiz. Move, get us at least